So let's do a few examples involving tangential normal coordinates as well as polar coordinates. So the first problem is using tangential normal coordinates. So let's say a particle is moving in some curve along a curved path, not necessarily a circle. And then the following things are given. I'm not going to write full sentences, but I'm just going to say what's given. Let's say it's given that the magnitude of acceleration so basically this quantity is given to be equal to 20 meters per second square. The rate of change of speed is given to be 5 meter per second square. The current speed is given to be 2 meters per second. And then the question is determine the current radius of curvature. Okay, so the magnitude of acceleration is given to be something, and then the rate of change of speed is given to be something else. This seems perhaps slightly confusing if you equate magnitude of acceleration to the rate of change of speed, but you want to realize that they are actually different quantities. The rate of change of speed is different from the magnitude of acceleration. So recall, first of all, that in tangential normal coordinates, as soon as people say radius of curvature, rho, you want to say tangential normal coordinates. And the acceleration expression, of course, is v dot et plus v square over rho en. Okay, and then the magnitude, this is the acceleration vector. And then as we just wrote down here, in fact, the magnitude of A, which is this quantity, is given to be, well, it's basically square root of sum of squares of the components. There's no square here. Okay, so that's given to be 20 meters per second square. And then the rate of change of speed is basically v dot. V is the speed, v dot is the rate of change of speed. And v dot is given to be 5 meters per second square. So that's why the magnitude of acceleration is different from the rate of change of speed. The rate of change of speed is just one part of the acceleration, as we have discussed before. The other part is the centripetal acceleration, which has to do with how the direction changes. Okay. Okay, so we know this quantity, we know the whole thing, and we know v, current speed, so that's v equals 2 meters per second square, 2 meters per second, I suppose. So we know the total, we know this, we need to find this, and that's it. So we can plug everything in. So we have phi square plus 2 square over rho whole square root equals 20. That gives us, squaring both sides, we can get phi square plus 4 square over rho square equals 400, or 4 square over rho square equals 400 minus 25, which is 375. And that's it, really. So rho square equals you bring rho square up, and then 375 down, you have square root of 4 square divided by 375, whatever that answer is. Okay, and in your exams, I do want you to compute decimal representation, okay, for homework and exams. And the reason why I say that is, yes, you're of course allowed to leave the answer as this, and we will give you full points if you do that. But it makes it easier for us to compare the answers to the correct answer if you actually provide decimal representation, because well, there are many different representations that might look like this. For instance, this might be 2 power 4. This could be, the denominator could be 20 square minus 5 square. You could write a lot of different versions of this that are equal to the same decimal representation, right? So, well, anyway, so I guess this is actually not rho square, but actually rho, because I've put a square root here. Okay, so that's the answer. For the purposes of this example, I'm not going to compute the decimal representation, but that's fine. So just to recap, we were essentially using an expression for the magnitude of acceleration, which has 4 quantities: this quantity, this quantity, this quantity, and this quantity. 3 of them were given. You were asked to find the 4th one, and I suppose you can do that by moving things around. So that could be one kind